Welcome everybody to Integrability Journal Club. And today I'm happy to introduce Matthias Wilhelm from Niels Bohr Institute, who will tell us about an operator product expansion for form factors. Please, Matthias.
Thank you. So let me start by thanking the organizers for this wonderful seminar series, for bringing us together in this times of pandemics, and for giving me the opportunity to speak here. So as mentioned, my talk is about an operator product expansion for form factors. Mostly I'll be talking about some series of work done in collaboration with Amit Sever and Alexander Tumanov. And the first of those appeared on the archive 3 months ago. In addition to these works on the integrability side, I'll also talk about a perturbative bootstrap of form factors. And this is work done in collaboration with Lance Dixon and Andrew McLeod. So let me begin with a short introduction and motivation to form factors. One quantity that has been studied a lot because it's very important in n=4 Super-Yang-Mills theory, as well as in other theories, is a scattering amplitude of elemental particles. It can be defined as the overlap of the vacuum with an n-particle on-shell outgoing state. Scattering amplitudes have been studied a lot due to the advent of the so-called on-shell methods, but also due to integrability. Another very important quantity in a conformal field theory like n=4 Super-Yang-Mills theory is the correlation function of gauge-element local composite operators ON. It is defined by taking the product of these operators at some positions xi and wedging this between two vacua. Correlation functions in n=4 have been successfully studied via integrability in the case of 2-point functions, 3-point functions, and more recently also 4-point functions. The form factor of a local composite gauge invariant operator O is defined by acting with an operator O at position x on the vacuum and then taking the overlap with an n-particle outgoing on-shell state. Now, if we Fourier transform the position of this operator to some momentum q, this momentum q does not necessarily square to 0, while the momenta pi do, of course. As such, a form factor is interpolating between the purely on-shell scattering amplitudes and the purely off-shell correlation functions. Note that momentum conservation now demands that the n on-shell momenta pi are adding up to the off-shell momentum q. Moreover, this operator is a color singlet, so the momentum q of that operator doesn't partake in the color ordering of the n external legs, which means that the planar form factor has the topology of a cylinder, not of a disk, so the same topology as we have for planar 2-point functions. There's a number of motivations to study form factors. One motivation is to probe the extent of the methods and structures that were found for scattering amplitudes. Now, these include, for example, recursion relations, color kinematics duality, on-shell diagrams, polytopes and Grassmannians, formalization in terms of a twistor action, as well as a connected description. And by now, there's overwhelming evidence that these structures do in fact extend to form factors, so they are pretty universal. A second motivation is that form factors yield renormalization group coefficients, such as the dilatation operator, anomalous dimensions, and via them also beta functions. This yields interesting data for integrability, but also, for example, for the study of the standard model effective field theory. Moreover, the so-called pseudo-Markov form factor, so for two particles, reveals the IR structure of scattering amplitudes. Accordingly, form factors were one of two different successful ways the non-planar correction to the for-loop cusp anomalous dimension could be calculated. Form factors are also directly relevant for Higgs physics at the LHC. So concretely, in the physical relevant limit where the top mass is large, the Higgs to gluons amplitude is described by the form factor of the Lagrangian. So this is the limit where you integrate out that top quark loop. It was found that the 3-point two-loop remainder of that form factor in n equals 4 super Yang-Mills theory agrees with the maximal transcendental part of the same quantity in QCD or pure Yang-Mills theory. Thus, n equals 4 can directly tell us something about Higgs physics at LHC. Moreover, this relation for the maximally transcendental part was shown to extend also to the next order in the large top mass limit. Finally, also integrable structures have been identified in the form factor at strong coupling via a Y system and also at weak coupling. The topic of today's talk will be to provide some integrability-based description for form factors at any coupling in an expansion around the near collinear limit. Moreover, I'll also mention how we can bootstrap these form factors perturbatively at any generic kinematics at 3, 4, and 5 loop order. Throughout my talk, I'll focus on planar n equals 4 super Yang-Mills theory and the MHV form factors of the chiral part of the stressed tensor supermultiplet. This supermultiplet contains the chiral part of the Lagrangian here. So the part that's actually relevant for the Higgs physics, but it also contains the operator built from two identical complex scalars, which is part of the famous 20 prime. The rest of my talk will be structured as follows. I'll begin by introducing this form factor operator product expansion, which expresses form factors in terms of only one new building block, something we call the form factor transition. I'll discuss some properties this form factor transition has to satisfy, which follow just from its definition, and allow us to bootstrap this transition at any coupling. I'll then continue with the extraction of the Born level form factor transition, as well as matching some initial data. Finally, I'll go to finite coupling before ending with the conclusion and outlook. At the heart of the integrability-based description is the dual picture in terms of Wilson loops. If we have a set of momenta pi here, we can define dual momenta xi by demanding that the difference of xi plus 1 and xi is equal to pi. So here illustrated for the case of the 6-point amplitude, we obtain a null polygonal Wilson loop. So it's null because the pi being associated to each edge of this Wilson loop is squaring to 0. And here at the cusps of the Wilson loop, we have the dual coordinate xi. Now, in the case of amplitudes, these n on-shell momenta sum up to 0. That means if we go once n steps, we arrive at the same point in dual momentum space. So we obtain a closed polygonal Wilson loop. In the case of form factors, the n on-shell momenta do not add up to 0, but to q. So after going for n steps, we don't arrive at the same point, but we are q away. So we have a periodic null polygonal Wilson loop. Now this picture is also very useful for seeing dual conformal symmetry. And in general, this periodicity constraint transforms as well under conformal transformation. So if it's a simple translation in one conformal frame, it's not necessarily one in any frame as well. So in order to make this manifestly dual conformally covariant, we can rewrite it in such a way saying that x of I plus n should be p of xi with some generic periodicity constraint. In the case of scattering amplitudes, the dual description in terms of Wilson loops has allowed for an pentagon operator product expansion, which makes it possible to express the amplitude or the dual Wilson loop in the near collinear limit at any value of the 't Hooft coupling via the integrability of the GKP flux tube. Our idea in this project was to develop a similar operator product expansion for form factors, now based on the periodic Wilson loop, and to bootstrap then and describe the form factors in a similar way. So as a first step, we decompose this n-sided periodic Wilson loop into n-2 pentagons. So here, these 3. And a two-sided periodic Wilson loop, this one here. Now, what we can associate this is we have a flux tube which stretches from 2 opposite edges of this Wilson loop. And we can think of this as starting with a vacuum on the top edge. And then this is propagating along the first square. And it's undergoing a pentagon transition via this pentagon here to an excited state of the flux tube, psi1. And this state, psi1, is then undergoing a second pentagon transition to a second excited state, and so on until finally the last, the n-2nd excited state, is absorbed via this two-sided periodic Wilson loop in what we call a form factor transition. Now, this operator product expansion for form factors has a direct analog for local composite operators in the operator expansion for the correlation functions of local composite operators. Here, this pentagon transition would correspond to a 3-point function or structure constant if you want. And the final step, the absorption by the two-sided periodic Wilson loop, can be thought of as a 1-point function of a local composite operator in the presence of a defect, something that many of us have recently studied using integrability. So this is really the main idea and the big picture. Now let me present some details. As you know, Wilson loop with cusps on its own is UV divergence due to these close distance divergences developed at the cusps. Now, in order to obtain a finite quantity, we can consider a ratio. Concretely, we take this n-sided periodic Wilson loop and we divide by the pentagons and the two-sided periodic Wilson loop here. And to avoid overcounting, we should then multiply by the squares in which these two and these two and so on quantities overlap. Now, that here is the general formula. Now, to each of these squares, we can associate some parameters tau, sigma, and phi, which are conjugate to the GKP twist, conformal spin, and angular momentum in the transverse plane. We can then use these parameters to parametrize the geometry of the Wilson loop. For the upper n-3 middle squares, which are the ones which are resulting from an overlap of pentagons, we can simply use the same definitions as in the case of scattering amplitudes. So here, tau, sigma, and phi are just different ways to rewrite the usual dual conformal cross ratios. In the case of the lowest square, the one that arises in the overlap here from the last pentagon and the two-sided periodic Wilson loop, we can define two dual conformal cross ratios. So they are written in terms of the momenta, the dual momenta x1, x2, x3, as well as also the periodic images here. Now, if the periodicity constraint P is just a shift, a translation, this here becomes a perfect square, but that's of course not the case in any conformal frame. Moreover, note that the angle phi here is vanishing in the case of the form factor, while it was of course not vanishing here. So we have one less cross ratio associated to this than compared to the 6-point amplitude. Now we have everything in place to make the statement of the form factor operator product expansion, which is the expansion of this ratio of Wilson loops dual to the form factor in the limit of large tau. This ratio is given by a sum over all eigenstates psi I of the GKP flux vacuum on each of these squares. Now, the summand is a sequence of pentagon transitions ending in a form factor transition. Moreover, for each propagation of the state across one of these squares, we have one such exponent. Here, E is the GKP energy, P is the GKP momentum, and M is the GKP angular momentum. These three quantities are in fact known at any value of the coupling via the integrability of the GKP flux tube due to the work of Benjamin. Moreover, these pentagon transitions here are also known at any value of the coupling. They could be bootstrapped using, again, the integrability of the GKP flux tube. That leaves us with only one new ingredient, the form factor transition here. It is universal in the sense that it only depends on the operator which we are looking at, but not on whether we are considering a 3-point form factor or a 300-point form factor. Moreover, it's reasonable to expect, and actually turns out to be true, that we can bootstrap this form factor transition at any value of the coupling. Now, this was really the main idea and statement of the form factor operator product expansion. Now we can look at the form factor transition and the properties it has to satisfy. But before that, I'd like to ask you whether there's any questions on this part so far.
Sorry, can you give more in terms of the form factor transition? Is there some diagrammatic definition in field theory, or it just totally can be understood only with integrability?
There's some diagrammatic definition, which is in 2 slides. And that is just the one in terms of Wilson loops as well. But the more intuition in terms of integrability is that it would correspond on the OPE side to the 1-point function in the same way that the pentagons are 3-point functions or structure constants. Any other questions? I'm afraid I don't see you if you raised your hand, so please just ask ahead if there's anything you want to ask. Okay. If not, let's go on.
Yeah, please.
Hmm?
Yeah, no raised hands, no questions, please.
Okay, great. Okay, so let's look at this form factor transition. So these GKP eigenstates that I mentioned before can be parametrized by the number of excitations n, the species of these excitations A, and the beta rapidities of them U. We can then define the form factor transition, and I hope this answers your question, Kolja, as the expectation value of the two-sided Wilson loop with these excitations inserted on the bottom edge, divided by the expectation value of the same Wilson loop, but now without the excitations inserted there. And this you can, and we will, at lowest order of Q, of course, compute by Feynman diagrams as well. But I'll come to that later. Now, from this definition, there follow a number of properties, constraints, or if you want, axioms, which this object has to satisfy. And we can indeed, as previously mentioned, use these axioms to determine the form factor transition at finite coupling. The first of these axioms is called Watson identity, and it's a property of the state of the GKP eigenstate.
So could you remind, so this beta roots, are they on top of the flux tube? This type of...
exactly. So we have the flux tube beta roots. Benjamin described the spectrum, and is this story where you start essentially with a spin chain where you have a lot of these covariant derivatives between any states in the usual spin chain. And then you can think of this as describing an extended object, a Wilson line or loop, instead of a local operator. But it's the usual spin chain based on the GKP string instead of the BMS string that we look at in the spectral problem for local operators. Okay. But one property of these states is that if we switch to excitations, we have to pay the S matrix for it. So that's the first axiom. Just by definition, via the property of the state, the form factor has to satisfy the form factor transition. there's also a second axiom, we call it the Singlet axiom, and that goes back to a property of this two-sided periodic Wilson loop. So it is manifestly invariant under rotations around the transverse two-dimensional plane, which is some U1 phi symmetry. But it's also invariant under the SU4 symmetry. So that means the form factor transition, which we try to determine, is also a U1 cross SU4R singlet. And now we can look at the different fundamental GKP excitations. So they're here scalars, fermions, antifermions, gluons with opposite U1 charge. And here we have these bound states. And they're shown here with the energy or twist and the different SU4 representations and U1 charge. And if you look at them, you immediately see that they are all charged under this U1 cross SU4R symmetry. So none of them is a singlet, but the form factor transition is supposed to be a singlet. So it immediately follows from this that the form factor transition cannot absorb a single particle state. In fact, now you can do a bit of combinatorics with the different quantum numbers, the energy, the U1 charge, and the SU4 representation. And you can figure out that actually only singlet states with an even Born level energy can contribute to the form factor transition. That means this expansion in the large tau limit, which at V coupling for amplitudes starts with e to the minus tau. For form factors, it really can only go in even powers of this quantity here. And unfortunately, this constraints makes the form factor transition also much harder to determine than pentagons.
So, sorry, for you probably it's very familiar, this Born, but could you explain like for poor people in London?
So just going back to this slide, so we're looking at the twist, so the energy, and for these excitations, we have twist 1, and then if you act with a covariant derivative, you increase the twist by 1. And then, of course, Benjamin found the all-loop corrections to the energy. So there's some Bethe-Ansatz techniques, some games you can play to determine the spectrum of these excitations at any value of the coupling. Does that answer your question?
My question is, what is Born level?
No. So at the practical level, you can have a list of all excitations here. And I can tell you that the Born level energy for this one is 1, for this one it's 2, for this one it's also 2, and so on. So it's just tree level, just no loop corrections. So as you would say that the SU, you would I guess say that the SU4 Kunishi has a Born level or tree level energy engineering dimension 4, and then you get 12G as the one loop correction, and then it goes on with the G square. Does that answer your question?
So it's bare dimension, in other words.
Yes, it's the twist. So the twist is the difference between the dimension and the spin.
Yeah, all right.
But yeah, because it's the difference between the dimension and the spin. For fermions, for scalars, you have dimension 1 and spin 0.
just total twist, or what is that? I just
no, just engineering dimension and engineering spin. I mean, spin has no corrections, but the dimension has corrections, quantum corrections, and you just kill the quantum corrections. You just say a scalar in 4 dimensions has a scaling dimension 1.
It's 3 level. That's what you say.
It's a matter of language. It's leading order in perturbation theory.
Yeah, leading order, coupling equals 0, engineering dimension.
When you talk about Wilson loops, sometimes people call it 3 levels, sometimes people call it 1 loop. It's leading order in perturbation theory.
Now I understand it, because I was thinking about Fermi level, maybe like Bohr had his own. But now.
Okay, well, good that you asked. But yeah, I mean, here it's just 1 because it has no spin, and the engineering dimension is 1. Fermions, of course, have engineering dimension 3/2, but a spin 1/2, so the difference is also 1. And for the field strength here, you have engineering dimension 2, of course, because it's the commutator of 2 covariant derivatives. But we have also spin 1, so also the twist here is 1. And that actually brings me to something I'll talk about later, that if we have even energy, and we have to have a singlet, there's obvious ways how to build such a state. We can take a combination of this one with this one, this one with this one, or 2 of these guys to form a singlet. But yeah, as I mentioned, more of this later. Okay. So much for the singlet constraint. The next axiom or constraint we have is a simple one to understand. It's a Z2 reflection symmetry, and it amounts to, if you have this Wilson loop, just looking from it from the other side, looking at it from the other side. And of course, that cannot change the physics, but if you look at it from the other side, of course, the order of all of these excitations does change, and also the direction in which they move is changed. So the sign of all of these beta rapidities is flipped.
But like from the picture, it's not clear that there is an equality, unless I missed something.
From this picture here.
Yeah, the right-hand side and left-hand side look totally different to me. Maybe I missed something.
So they should be just the mirror image. Here, if you here have an axis, and you just look at the mirror at that axis. So just, yeah.
So perhaps I just don't understand. So when you draw a line, what it means? So one of them is what? Is a light cone direction, right? The one where magnets live. And then the one where there are no magnets is what? Is this just shift?
So, okay, so let me go to this here. So this direction is the sigma direction, and this direction is the tau direction.
I guess it would be more clear if there was another reflection in the picture, up down.
All right. Okay. Yeah. That's
yeah. But I mean, the reflection is at this. I mean, you can place a mirror here, and consider this to be the mirror image of that one. But you can just, I mean, if you look at my hand and you look at it from this side and I look at it from the other side, of course, the physics cannot change, and the physics here happens in this 2-dimensional plane. So.
Sorry, and another, just to understand this question one and forever. So why there are magnets on this horizontal, let's say, line, but no on vertical?
So you could, of course, mirror transform them to any line you want, but it just starts that way because we are looking at this Wilson loop here. I mean, you can even draw it for the case of the hexagon, and now you decide that you want to tessellate it in a certain way, and you start here on this edge with the vacuum, this is the picture I had before, and now you have this flux tube that stretches from this edge to this edge, and it propagates this way. So you consider this one to be the endpoint of this flux tube, and then the flux tube excitations end up on this line. So it's you can show it here as well. It's this picture. So this flux tube state psi1 is starting off as the vacuum here, propagating to this edge along the first square and so on. And then we consider here some excitations at these positions. Now I should tidy up all of the screen painting. Is that clear?
Yeah.
So form factor is about some given operator, and the information about this given operator is exactly that beta roots on the bottom. How is encoded information about particular operator?
So far, it won't. I think it's encoded in how you solve the form factor constraints. So far, there was no information.
Yeah. So far, I mean, the information about the operator is really encoded in this periodicity constraint. So, for example, in this case, it's the easiest case we started looking at, of course. So here the operator has a momentum q, and that information is encoded here in the periodicity constraint. But in principle, we could also look at a, say, charged operator or some operator with some other set of non-trivial quantum numbers, and then they should be encoded in this periodicity. So
the operator for you is always BPS in any case, so there are no beta.
So in this case, it's a BPS operator. So here it's really trivial, not much additional information except for this one.
Right, trace of z square or half BPS.
Yeah, so it's this operator here. So you can look at it in superspace, and you could write it as in terms of some x and chiral coordinates. But then
information on which of those you consider will be encoded into a particular solution for the form factor.
Yeah, but I mean, here in this case, one encodes all of them at once. So it starts as the lowest component with a z squared, and as the highest component, you have the on-shell Lagrangian coming with a theta to the fourth. So since this is half BPS supermultiplet, we're looking at the chiral half, we can describe all of the operators in the supermultiplet at the same time.
But if I want trace of z to the L, can you do those?
We started looking at it, but we haven't any concrete results yet.
There would be no difference in what you said, right? In what you said so far, there would be no difference.
Mostly yes, but this here, I mean, this part here doesn't have any charge. So there's no charge, nothing non-trivial in the periodicity constraints. But the difference between z squared and z to the L should enter this periodicity condition. But yeah, I mean, what you asked, Evgeny, is this here is just a property exactly of this GKP flux tube.
Well, I actually asked about encoding information about this operator, and you say that it is in this periodicity function file.
Yes.
And will you show us any example of this file like later?
But wait, periodicity is the momentum, right?
Yes, it's the momentum in one conformal frame. But if you have the momentum is a translation, and you do a boost, and you do some dual conformal transformation of a momentum, it's no longer a momentum. So momentum isn't really dual conformally invariant description, because in another frame it looks differently.
It doesn't encode everything you like about your operator, just momentum in your Fourier. So
well, this is kinematics, right?
Maybe I can comment.
Sure, Amit?
The operator we are considering only has one non-trivial charge, which is the momentum, which under T-duality becomes translation. This is the periodicity.
Yeah, but just one wants to consider a more generic operator. So far, what was explained is no difference to my impression.
Yeah.
Right. But for the diagrammatic level, so the definition of the operator, the difference would be that when you go to the next block, you also apply other symmetry transformation, that is the T-dual of the charge of the operator.
Yeah. So I mean, you can look at it with the transfer matrix, say, and I mean, this is something I did in this paper with David Drittimann and Ruven 5 years ago, where you act with the transfer matrix, and then you have some conserved charges, and you can pull that transfer matrix from the external legs all the way to the operator. And in the case of this half BPS operator, it's entirely trivial, but for other operators it would be intricate. And then, as Amit said, that should be encoded in what happens if you go from one point to its periodic image in the dual space.
Say if I have any SU2 operators, then there won't be any difference, right? Because on the translation there won't be any non-trivial transformation. So what you said for SU2 sector or SO6 is still
I think the moral story, if you want, here is really the one picking up the Lagrangian, because this Lagrangian, it's just two gluons, so there's no charges, but it just happens that the Lagrangian is in the same supermultiplet as z squared, but then, because we're looking at the whole supermultiplet, it happens to describe something in the SU2 sector, but that's not necessary. And it's not the case that f, I mean, the Lagrangian, of course, contains f squared, and f squared is related to z squared, but f cubed is not related to z cubed. So then we have some real charges.
Just I want to confirm. So what you said so far at the level of the pictures would suit any SU2 operator. Is it correct?
No.
No?
Okay, maybe we will clarify it during coffee break.
At the level of the axioms, they will be the same, apart from the Singlet SU4 and take charge. But
yeah, I mean, the axioms, yes, but not this fact that the periodicity is just shift. But yeah, I mean, the axioms, they would all be the same.
Yeah, so everything is the same. I don't see why shift, but let's discuss over coffee break.
Okay, let me just clean that piece here. Okay, so
can we pause for coffee break? Matthias, what do you think?
Sure.
Ah, great. Then let's stop recording.
It's coffee break, so I can continue.
Okay, then let's continue with the discussion.
Oh, sorry, I don't understand about translation. Translation, if it's SU2 operator, is still translation. There is no extra transformation on top of that.
But you have some...
operator, all you said is still the same. Then Oh, recording should stop, sorry.
Yeah, let's start the second part. Matthias, please.
Thank you. Okay, so we already discussed 3 of the axioms. Now there's a 4th axiom as well, and that is related to the square limit. So it's informing us about what happens if the first excitation has a rapidity which is very similar to that of the last excitation. Now we can look at that situation in position space on this lines, as we discussed before here. This is the sigma direction, this is the tau direction. And one way we can have very similar rapidities if the first excitation is very much to the left and the last one very much to the right, such that these two are close to each other's periodic images on opposite sides of that edge here. So in this situation, the two decouple and the position space form factor transition factorizes in the product of the square transition of these two excitations and the form factor transition with these two missing. Now, this gives this term here in rapidity space, but there's actually another way to arrive at that situation in position space, namely if this here is to the very right and that one, the last one, is to the very left. But in addition to the previous factor, we then also get a lot of S matrices we have to pay in order to rearrange the excitations as such. Now, in the interesting case where there's only 2 excitations on that edge, you see that this here is unity, and the different signs for bosons and fermions, as well as in these S matrices then, lead to, together with this I epsilon prescription as well, leads to a delta function for 2 fermions and 2 gluons, but to a principal part prescription for 2 scalars. Now, the last axiom is crossing. So crossing means that if we are starting with an excitation at the first position and we're doing 2 mirror transformations, we are ending up at the last position. Now recall that a mirror transformation is simply sending the momentum of an excitation to I times the energy and vice versa. Okay, so here we have now discussed all of our axioms, and in principle we could now try to bootstrap them. However, that turns out to be quite complicated, so we'll start with Born level, and there I'll also tell you how exactly it happens that this is quite complicated. So at Born level, tree level, lowest order in perturbation theory, however you want to call it, the leading weak coupling contribution in the OPE limit, which is the tau goes to infinity limit, starts from the states with Born level energy 2, and it has to be singlet states according to the singlet constraint. And because this is a 2 here, it means we can have 2 particles, and that means sigma couples to the sum of their momenta. So that makes it much harder, because if it would be just 1, we could hope to recover the U dependence from the sigma dependence by some Fourier transformation. But here it's impossible to recover the U1 and U2 dependence just from the data. So in fact, there's 3 different such singlet states with Born energy 2 built from 2 excitations. And as I hinted at before, they're built from having locally fields F and F bar at position sigma 1 and sigma 2, psi and psi bar at positions sigma 1 and sigma 2, and phi bar at positions sigma 1 and sigma 2. And these states are, or three of them are linear combinations. And here we label the state by the asymptotic leading contribution. So if we have the two excitations on the line being very far from each other, only one of these combinations, phi bar, psi bar, or ff bar is leading, and this is the one we use to label the state. But of course, for finite separation, all three of these coefficients are contributing, and these coefficients are what you would also call the wave functions. Now, unfortunately, the wave functions weren't available in the literature, so we had to calculate them ourselves by diagonalizing the dilatation operator, or the Hamiltonian, or rather diagonalizing the transfer matrix. And this transfer matrix mixes these three components in a highly non-trivial way. So what we find in the end is some intricate combinations of hypergeometric functions. I should also mention that there's in principle a possibility for two one-particle effective excitations to contribute, but it turns out that they are just not contributing and non-vanishing outside. Now, to calculate the form factor transition in position space, we just have to connect such an excitation with its periodic image with a propagator. So we just have this propagator where here sigma 1 and sigma 2 are the positions of the two excitations, and S is the conformal spin, and you recall that it is equal to 1/2 for the scalars, 1 for the fermions, and 3/2 for the field strength. Okay, so now we want to go, of course, to rapidity space, not to position space. So we convolute these propagators here with the wave functions that I showed you on the previous slide, which are determining the states in terms of the fields.
I'm a bit confused. So what you do now, are you doing in perturbation theory with?
Yes. Now I'm doing the Born level form factor, the leading order in perturbation theory, just to get started.
But not because axioms, but rather just computing it directly. That's what you do.
Just by a hardcore combination of field theory and integrability techniques to diagonalize this transfer matrix, to diagonalize the Hamiltonian to determine the states. So of course it would be nice to do it via axioms alone, but I mean, maybe if I present to you the results at hindsight, you'll be able to do so, but we at least were not able to. And one reason you cannot directly extract it from the data, I mean, that would be another option that we tried and didn't manage to do either, is from the data, but the data is only in terms of sigma. And now we want to determine a function of 2 parameters from a function of 1 parameter. It only couples to the sum, not to the difference. So there's no clear way how to do that. There's some loss in it. So it's much harder than in a situation where we would just have one leading state contributing, which would have one excitation, and then we would be able to do some Fourier transformation to get it from the data. But here we have also these 3 things with the same quantum numbers. So it's really a complicated sum of things.
What you're saying is that the set of axioms you have is incomplete, or is it just very complicated to deal with? Which one?
I'm saying we weren't just clever enough to do it just from the axioms. But so if you after seeing the axioms will be able to tell me this the solution at this point, I'm very happy to draw my head, but it's just not easy. I mean,
but my question is simpler. So okay, one thing is to solve it, another is to be sure whether there is some kind of uniqueness.
Yes, and there's, I mean, we are making some checks to make sure that there's some uniqueness. So I come to that later. But we have some match up to 5 loop orders. We have some match with a minimal solution at strong coupling. So, I mean, if once you have a match up to 5 loop orbiters, there cannot be a question about whether you're looking at the right thing. But just from the axioms, without any input from data, it doesn't look like you can do it. So we need a minimal amount of data. I mean,
So
I'll tell you more about that later.
3 level into and axioms together, and then you will be able to get unique solution. Is what's going to happen?
I'll need a little bit more data, and in approximately 5 slides, I can tell you more if I arrive there before the end of the time. Okay, so I hope you're okay with deferring that answer. Okay, so as I mentioned, these wave functions that we are convoluting are rather horrible looking, involving a lot of hypergeometric functions. But once you do that calculation and all of the dust settles, and there's a lot of dust to settle, you arrive at that simple answer for the Born level form factor transitions. So you see for all of them, you've got some delta functions because they have to be singlets. And then for the scalars, we have this simple ratio of gamma functions. I mean, maybe Kolja could have told us that before, but at least we couldn't figure it out before. But you can check that this, of course, satisfies all of the axioms. And then for the fermions and for the scalars, we have only delta function support. So they are vanishing unless the momenta are different. And the coefficient here is the inverse measure. So this is something that has to be there according to the axioms. But there could be also other stuff with non-delta function support that would be a problem for factorization for more than 2 particles. But at that point, it could be more complicated. But here, this is indeed the simplest solution to the axioms. So now that we have the solution at leading order for the form factor transition, we can, of course, match it with data to check that we are on the right track. And here we can extract from the one loop form factors that were calculated by the Green-Merrill group 10 years ago, the one loop ratio of Wilson loops, which is this 2-line expression. And we can expand it to the leading order in the large tau limit. And we find a perfect match with the form factor OPE. Now we can even do better just with the Born level leading order form factor transition. If we carefully study the structure of this OPE formula. So if you look at this here, you see that the only source of polynomial terms in tau is corrections to the energy. So the energy, as known at all loop orders, thanks to work by Benjamin. And if you have, of course, some correction here at loop order, you bring down tau. And in particular, you see that if you have L-1 powers of tau at L loop orders, it means that all additional powers of the coupling squared have to come from the one loop energy. So that means the Born level form factor transition provides the L loop terms tau to the L-1 at any loop order. So now in order to check that against data, we have to translate the ratio of Wilson loops to the remainder function, which is the more conventional way to express loop corrections to form factors. But that can be done to any loop order. And it requires the one loop expression for the ratio, which I showed you on the previous slide, and the cusp anomalous dimension, which is of course known at any value of the coupling. Okay, and now if we do that, we find a perfect match with the two-loop remainder function that was determined by the Green-Berry group at this order tau to the first e to the minus 2 tau. Okay, so now let me switch gears and tell you a bit about finite coupling. So the simplest solution, and now the name of the game is, of course, to use the axioms to solve these form factor transitions at finite coupling. So just solving the axioms, essentially. But as you'll see, there's a need for some data. But we observed at Born level that the fermionic and gluonic form factor transitions were equal to a delta function times the inverse measure. And now the simplest solution at any coupling is also exactly that. And in fact, we get a problem with factorization if we pick another solution. And you can also try to solve the axioms for other solutions, even in the case of just two particles. Then you get something really ugly. You need like logarithmic cuts instead of square root cuts. So really stuff you don't want to go to. Okay.
Sorry, these two
Yes.
functions, do you solve independently for them, or they kind of enter into coupled system?
The axioms by themselves are not coupled, no. But of course, if you match with data, it's coupled because the data is the sum of the three contributions.
When you go to multi-particle.
Yeah, when you go to multi-particle, then they do occur together, and I'll have a slide about that towards the very end. Okay, and now coming.
Yeah. Yes, the word simplest means in sense of analyticity. Yes, no extra cuts and so on.
Yes. I mean, if you just look at this, if you ignore the multi-particle factorization business, you would otherwise need to introduce some logarithmic cuts, which are really unnatural, and that's just not something you want to go into. But I mean, we match the data, as I'll tell you soon, with just that. But I mean, strictly speaking, if you want to make the crossing symmetry manifest, you should rewrite this delta function in terms of the momentum of the particles instead of the rapidity of the particles. But then, now coming back to the question of uniqueness, for the scalars, the solution to the axioms is not unique. And the way forward then is that we can actually parametrize the freedom in the solution. And we can then try to fix the parameters via data. So now there's no data beyond two loops for the 3-point form factor. So our solution is to, of course, make our own data. And one very effective way to get data for the 6- and 7-point amplitude is the perturbative bootstrap. It has been used to determine the 6-point amplitude up to 7 loops and the 7-point amplitude up to 4 loops. The rough idea of how the bootstrap works, if you haven't heard this story before, is by understanding which functions your answer has to be written in terms of. And if you understand that function space, you can make an ansatz, and then you can fix the coefficients in this ansatz by physical constraints, such as those coming from the OPE.
So could I ask if, can you squeeze some data from, say, sending Q to 0 and then interpreting this as a derivative with respect to coupling of just an amplitude? Or it's trivial?
Possibly, but we haven't tried. So that's not something we looked at.
Can I add something?
No.
But, okay, no, if you set it to 0, I mean, if you had it to 0, you're in the situation of amplitudes because it's no longer periodic. But okay, what was your comment, Amit?
It's a bit of the degenerate limit. Our background is the two edges, two null edges. Two null edges in different directions cannot be closed. So it's a very degenerate limit, expansion point.
Okay. Yeah, we found another way, and I might be tempted to argue in a more interesting way to generate data. So I teamed up with Andrew McLeod and later joined by Lance Dixon to do a perturbative bootstrap of the 3-point form factors at so far 3, 4, and 5 loops. So that would be a story for a talk on its own. So since this is an integrability audience, let me just describe how it interacts with the integrability story. So here I've shown the table where in the first slot I have the loop corrections. So this is 1 loop, 2 loop, 3 loop, 4 loop, 5 loop. And in the second slot, I have the powers of tau. So this is tau to the 0, tau to the first, second, third, fourth, and so on. Now, as I mentioned before, the leading order form factor transition here determines the leading order contributions in tau at any loop order. Now, the Green-Merrill group has calculated the 2-loop remainder function some 8 years ago. So from this, we know also the tau to the 0 terms at 2 loops. Now, they are in fact sufficient to completely determine the unfixed coefficient in the solution to the axioms for the form factor transition at next to leading order. So here the n is always the exponent of the n in next to leading order. So the next to leading order form factor transition then determines the next to leading order terms in tau, again at any loop order. But now we have the leading and the next to leading order in tau for the 3-loop form factor. And that was in fact sufficient to bootstrap this form factor perturbatively, which then gives us also the tau to the 0 terms at 3-loop. But the tau to the 0 terms are now sufficient to completely determine the form factor transition at next to leading order, which is then yielding all the next to leading order tau terms at any loop order. But then we had the first 3 leading orders in tau for the perturbative bootstrap, where this was sufficient to determine all coefficients in that perturbative bootstrap and determine all of the for-loop form factors, in particular this tau to the 0 piece. And you know how it's going on. That is determine the next to leading order form factor transition, which determines the respective order in tau at all loop orders. And in principle, we could go on like that forever. But in fact, by the time we were at for loop, I was able to spot the all loop pattern in this form factor transition. So let me briefly tell you about that.
Could I ask, so when you say perturbative bootstrap, is it making ansatz out of some functions and then imposing some
Exactly, it's exactly that one. So you might have heard a number of talks by these authors on that subject for the case of scattering amplitudes in the last 9 years.
And you state that number of functions for tau zero term do not grow with loops.
Pardon?
So tau to the power 0 terms, number of functions multiplying these terms do not grow with loop order. That's what you're saying.
What I'm saying is that so far there were always enough constraints to completely fix all coefficients in the bootstrap, the perturbative bootstrap, from lower loop integrability data. So in both sides of that game, we are making a bootstrap, but we can go up, let's say, a ladder in the way I tried to explain here, by always only using one lower loop order on one side to get the full result at the next loop order at the other side. And then you go up with one leg on the one step and the other leg on the other step until you are all the way up in loop order. Or in this case, until at for loop order, I was able to guess the all loop pattern. Okay, so coming to that all loop pattern, recall that for the pentagon, the all loop structure of the pentagon transition creating two scalars, scalar anti-scalar, is equal to the tree level value. And then you have some exponential of some source terms that are evolved with the BES kernel. So if you are very familiar with this story, those are the F1, F2, F3, F4 functions of Benjamin and friends. Now, what we found for the form factor transition is that here the corresponding exponential is evolving source terms that are also evolved with the octagon kernel. So the octagon kernel is, of course, well known from the octagon, but it also occurs for the origin of the 6-point amplitude. Now, so far, it is completely unclear to us why this octagon kernel occurs in these three seemingly unrelated physical setups. Maybe there's a deep reason behind this, but maybe n equals 4 super Young-Mills theory is just lazy. But using this kernel, we can match all the data up to 5-loop order. And we can also see that this matches the minimal solution to the axioms at strong coupling. So at strong coupling, you have that SO sigma model, and you can solve the axioms for that one, and you arrive at the same solution at strong coupling. Okay, now finally, let me also talk about higher contributions in the OPE expansion. So far I talked about the leading order, which is the order of e to the minus 2 tau, where we had only 2 excitations in a state contribution. But
so you have this exponent time any polynomial factor currently, is
it? What are you asking about?
So you compute all contributions which are of the exponent times some power of tau, basically, right, to any loop order.
Yeah, but this was always for the leading order, so always for x of minus 2 tau. So previously it was always this term multiplied by a polynomial in tau. But now we can also go to higher orders in the OPE, where we have now also in 4 particle states, and 6 particle states, 8 particle states, and so on. Does that answer your question, Kolja?
Yeah.
Great. So what we find, however, is that the form factor transitions for these states are always given by a simple factorized ansatz. So factorization is also something certainly you would expect for integrability. And for the example of gauge field, fermion, anti-fermion, and anti-gauge field, so gauge field with the opposite U1 charge, you find this simple factorized result, which is just the product of the F bar form factor transition for two particles and the fermion anti-fermion two particle form factor transition. And again, we find a match with this to quite some non-trivial loop orders. Okay, now let me come to a conclusion. We have proposed an operator product expansion for form factors based on the dual description in terms of these periodic Wilson loops, and that expresses them in terms of only one new building block, the form factor transition. I've showed you how we have bootstrapped with a sumhead from data this form factor transition at finite coupling. Now, this opens the door for studying form factors in the near collinear expansion at any value of the coupling. At the same time, we have bootstrapped these 3-point form factors for general kinematics at 3, 4, and 5 loop orders so far. And this is the case relevant for the Higgs physics. So they are giving the maximally transcendental part of the Higgs to 3 gluon amplitude at LHC. Now, as mentioned, everything so far was about MHV form factors of this chiral part of the stress tensor supermultiplet. It would also be interesting to go beyond MHV to a situation where we expect to encounter charged form factor transitions in the same way that for amplitudes beyond MHV, you obtain charged pentagon transitions. Moreover, as I think was thoroughly discussed by now, it would also be interesting to look at other operators, but you have to stay tuned to learn more about that. Thank you very much for your attention.
Thank you, Matthias. Let's unmute ourselves and thanks. Now we have time for a few questions, comments.
So what happens like at finite coupling is this? So you computed, say, exponent of tau times some polynomial, right? So I guess at finite coupling is a bit hard to distinguish one from another, right? So is it impossible to tell what you compute at strong coupling thing?
So, I mean, it would be, this is something I have not on the slide, but it would, of course, also be interesting to look at strong coupling and see how we reproduce this Y system of Mandlasena and Zubodov there. And a general, of course, the formula looks like this. So you only get polynomial terms in tau, but
I mean at weak coupling.
at weak coupling, if you're really doing this expansion here. So if we are just considering this to be some number, which it is at finite coupling, then the degeneracy will be lifted. So there will be different numbers here, and they will, yeah, there will be the gluons contributing as what we expect at strong coupling.
But none of this goes to, say, 0 at strong coupling?
The scalars go to 0.
So you will have to kind of resum all the contributions?
Yeah, and then you could think about doing storage with resummation, but that resummation for the case of amplitudes has only been possible at low loop orders. We're talking one loop here or tree level for NMHV. And then you could, of course, go to special kinematic points. And there's some points like this origin where it has been possible to actually resum all contributions. But that origin is one specific point in kinematic space. And for general points in kinematic space, of course, there's some of these are leading contributions and some are not. But there isn't a way, to my knowledge, to get a complete resummation of this at finite coupling for generic kinematics.
For finite, of course, but at strong coupling, can you do that at strong coupling?
That would be interesting, but we haven't had a chance to look at that yet.
You should be able to in analog to the amplitude case, and if they were able to sum also the scalars.
Yeah, I mean this Y system that we'd like to make contact with is quite similar to the Y system also for the case of amplitudes. So it should be possible to make the connection in a similar way as was possible for amplitudes.
More questions?
Sorry, Matthias, maybe a point along the ones that were asked. In the beginning that you mentioned, how much is known, by the way, about this supersymmetric extension? I mean, as you mentioned, suppose instead of MA3, you consider some supermultiplet and then look at this supersymmetric or super Wilson loop formulation. Do you have, is there analogous, is it straightforward to extend to some super axiomatic description? Or
so this is essentially already looking at the whole supermultiplet at the same time. So one way you can look at this is you can look at harmonic superspace, and then you do a Fourier transformation also in the super momentum. And then you get, since you're in a chiral superspace, you're only looking at the chiral half of this supermultiplet. You can get super momentum conserving delta function, which also involves the super momentum of the operator, but you're just factoring that out. So the duality is essentially looking at the ratio of the loop level by the tree level form factor. But that delta function occurs in both. So we are able to describe both the trace Z squared, which is the lowest component in the stress tensor supermultiplet, and the Lagrangian, or the chiral part of the Lagrangian, which is the highest component at the same time.
Maybe to add to your answer, super Wilson loop is what you get when you study non-MHV amplitude.
Sorry, I mean, can you repeat the last?
The super Wilson loop you would get if you would study also non-MHV amplitudes.
Okay, I see. But sorry, Matthias, it is, so you said this is momentum superspace, but is there any role plays the momentum twistor space or not? I mean, like complex projective extensions, or?
I mean, you can beautifully formulate all of this in super momentum twistor space. So yeah, that's also what we used in this paper with the Grossmanian story. What was it? Yeah, so this paper with the Grossmanian story, that we used that as well. And yeah, I mean, here you could, at this point, for that particular operator, also do this super Fourier transformation, and you get the delta function. And I mean, at tree level, I didn't mention that, but that quantity at tree level is just given by a very similar expression to the one for scattering amplitudes. So you have some Park-Taylor factor, and that is for higher MHV degree multiplied by some R invariance. So these 5 brackets. So yeah, if you look at these results, they will be looking very reminiscent to the things you know.
I can imagine. Yeah, maybe can you quickly recap? It's probably also related to Nikolai, what was asking. What is the actual complication of solving the axiomatic system directly? I mean, since you mentioned that it is an uncoupled system.
In solving the axioms. So one solution. I mean, one problem is that there's not a unique solution in the sense of, okay, I mean, if you now proceed, I mean, you'd say you open that paper of Amit, Benjamin, and Pedro from 2014, and you look at how they solved the axioms there, then you can try to solve the axioms in exactly the same way, and you find a solution, and then you compare it to the data, and that's what I did, and I found that it doesn't reproduce the data. So then I thought, I mean, can there be more? And the answer is yes, there can be more. And
for example,
the more that there can be, sorry, yes?
Yeah, sorry, I just thought, because in addition to that, you started briefly mentioning the measures appear in the denominator.
Yes.
Yeah, so can we comment on the structure? What could be this more? I mean,
so I mean, here there's here you could have something with a non-delta function support. So you could have, I mean, this is a delta function imposing, I mean, only non-vanishing for u equal to v. But you could have a small bump where u is equal to v plus 1 or something. I mean, nothing is forbidding that, except for the solution would look highly unnatural. Because it would need to have not a square root cut, but some logarithmic cuts, and we don't really encounter anything but square root cuts if you're looking at the spectral problem. So this is really strongly hinting at the fact that here these are the right solutions. The more dramatic freedom in solving the axioms is here for the scalar form factor transition. So in the solution that we found to reproduce the data, we have this terms evolved with the octagon kernel. Sorry, here they are. And these terms with the octagon kernel are entirely optional from the point of view of the axioms. If you don't have them, you're still satisfying the axioms, but you're not reproducing the data. So in principle, you could give them any prefactor, but the prefactor is fixed by requiring to match the data.
Does the same applies to the original pentagon transition?
I mean, I'm not an author of those papers, but my understanding is that there it was mostly the easiest solution that turned out to be the right one. Whereas here, the easiest solution didn't turn out to be the right one, and we had to look further. But maybe Amit can comment on that.
There is no proof of uniqueness. You know, when you get a solution, you are happy. But maybe to add what you said, if you go back to the square transition axiom, you see the product of all the S matrices there in the middle. So as a result, you cannot have a factorized ansatz for multi-particle unless the gluons and fermions are only supported on the delta function. Because for scalars, all this product exactly cancel out. And for the other ones, if they pair together, they become effectively, they also cancel out if they pair like that. And this is the only way that this axiom would allow a factorized ansatz for multi-particle.
They cancel between what and what?
You're taking two excitation, one for the right and one for the left. So you have a product of all S matrices both sides. So for scalar, when they scatter with each other, the rapidities are equal, this becomes just permutation. You can unwind it.
I see.
Otherwise, they don't. But if the other one come in pairs, you can also unwind them.
But then if you have more scalars, do you still, well, I mean, you have the ansatz that factorizes in terms of smaller number of particles, the expectation?
Yes.
Yeah. It's not as simple as a single factor, but.
Okay, other questions?
Yes, I have a question.
Yeah, please.
But you explained that for this form factor transition, you use the kernel of the octagon, right? As I remember, Benjamin introduced this kind of twisted kernel that has an angle, and
yes,
yeah, this angle. Well, he discovered that there are 3 values that
yes,
correspond to certain anomalous dimensions. So I was wondering
yes.
if you are finding more values for this angle within this context of the form factor.
So the 3 values you mentioned are the untilted one, which is giving just the hexagon. And I mean, indeed, the hexagon kernel occurs in this problem. So I didn't explicitly mention it here, but here you have the BES kernel plus the octagon kernel. But the third angle, which reproduces the hexagon anomalous dimension, that one doesn't appear in the problem. So, I mean, at least not to 5-loop order, but if it's not appearing up to 5-loop order, it's, I guess, safe to assume that it's not appearing.
Do you think the angle is related to other transitions? Like I can see that you are choosing the transition of scalars. If you include their fermions, maybe does that modify the kernel? Or, I mean, do you have an interpretation for this angle in this context?
I have a very technical interpretation of the kernel, which is related to satisfying crossing symmetry. So one of the axioms we had to satisfy is crossing symmetry. And if you're wrong direction, sorry. So if you require that essentially this analytic continuation, which in the case of rational functions is just adding 2i, that this leaves the object invariant, you cannot you cannot parameterize some freedom in the axioms just using the BES kernel. Because if you look at these functions, F1, F2, F3, F4 of Benjamin and friends, they have some non-trivial behavior under crossing. So to build some analog of these functions which are invariant under crossing, we need the octagon kernel. Because you recall that in this octagon kernel, the even part only talks to the even part and the odd part only talks to the odd part. So at the technical level, yes, we do understand why it's the octagon kernel occurring here, but in terms of intuition or physical interpretations, not yet. Does that answer your question?
Yeah, thank you.
Sorry, Matthias. Женя, go ahead.
No, I just wanted to say that if no other question, but
Okay, no, just a quick point that maybe, so essentially you BAS kernel provides you the constraining properties crossing, and is that the point that you are not getting what would be the analog constraints from the octagon kernel, or there is more than that?
Okay, to try to rephrase it, the octagon kernel is the solution. I mean, any multiple in this particular way of the octagon kernel is a solution to crossing as well as the other constraints. So it's the part which is not uniquely fixed by the axioms. It's where I can put a prefactor, and any prefactor of that will still satisfy all of the axioms, but just one prefactor will match all of the data.
I see, yeah. I see the ambiguity, okay. Yeah.
So maybe we should close the official kind of part to let people go and stop recording. Should we?
and let's thanks Matthias again.